I'm Charu Dixit.
I'm Akib Siddiqui.
And I'm Ali Shahzan.
We are final year electrical undergraduates at Aligarh Muslim University, and we are here today for the video demonstration of the project Maximum Power Point Tracking based Solar Micro-inverter for Photovoltaic Applications as an entry for Texas Instruments India Analog Design Challenge 2015. More than a century after its launch, Thomas Edison would still recognize today's power grid because it hasn't changed all that much since Edison and Westinghouse debated the design of original grid. Sure, we have increased the reliability of power distribution. In fact, with the confinements of current push-to-torque infrastructure, we did okay, but we are approaching the grid's capacity and okay isn't enough. Today, we can redefine energy with the way we use, manage and distribute energy. With the increasing demand of fossil fuels to nurture the ever-increasing energy requirements by man has led to the depletion of coal, which is a major source of electricity production. Hence, there has been increased focus on development of renewable and eco-friendly technologies in recent times. Solar energy is the most abundantly used renewable energy. India has a vast potential for trapping solar energy. Most places in India get sufficient insolation for about 8 months a year. But the existing methods of trapping the abundant solar energy and translating the available solar energy into commercial energy are ineffective and inexistent. In our project, we are going to provide a solution catering to the above problems. The project is about developing a solar microinverter with added features of MPPT so that the proposed product goes beyond the tappings of a typical inverter and provides a smart solution for providing effective electrical energy for domestic off-grid and or grid-connected consumers. It will empower consumers for making smart energy choices as they manage their energy costs and environmental footprints.
The project is broadly divided into two modules, the Maximum Power Point Tracker and the Solar Microinverter. An ability to harvest the maximum amount of energy from a photovoltaic array is one of the small number of critical features a PV system can offer to help optimize return on a PV system investment. It is important to note that when compared with conventional methods of generating electricity, PV generates a mere 0.2% of total electricity. There is a huge potential of increasing the share of electrical energy generated by the PV system, not only through expanding the installed capacity, but by increasing the return of investment on such PV systems. We are proposing the use of modular MPPT based microinverter which tracks the maximum power point for individual panel and inverts the power resulting from individual PV modules. This ensures that substantial amount of energy is saved. The MPPT developed is based on perturb and observe method. The control interface circuit for exercising control to achieve maximum power point is a boost converter. The solar power output is given to boost converter through Hall effect sensor and analog voltage sensor. The sensors are interfaced to a MSP430 board which calculates power at each instant by multiplying the two quantities. Based on the polarities of incremental power, the switching of MOSFET switch of boost converter takes place according to PNO algorithm. The output of the boost converter is given to the inverter for subsequent stages of project.
The next module of the project is the microinverter. Microinverters have assumed greater importance in recent times due to the fact that they exercise greater harvest efficiency as compared to the entire string system. Microinverters, when endowed with communication, can help in effective monitoring, managing and utilization of electrical energy. We have developed SPWM for our project. The basic advantage of SPWM inverter is that to filter out the harmonics, the size of RC components is reduced considerably. To implement the logic, we require a sawtooth generation circuit implemented by using LM555 IC of Texas Instruments. We require 450 Hz sawtooth wave, so that the first harmonic component that is present in the output wave is of 450 Hz. We need a reference sinusoid wave for ascertaining the frequency of output wave. The signal is taken from the grid. Op-amp based comparators are used for generating the switching logic for MOSFET drivers, which are connected in the form of H-bridge to invert the DC into the AC. Finally, RC filters are used to filter out the harmonics, resulting in the output of the PWM wave, which is a pure sinusoid.
We are here for the demonstration of maximum power point tracker. Perturb and observe algorithm is employed for the implementation of MPPT. We have implemented a boost converter as the interface circuit. Varying the duty ratio of the boost converter based on the values of incremental power, the duty ratio of boost converter is ascertained. Let us have a look at the circuit components of the MPPT. This is a 12 watt PV panel. This is the current sensor. It is interfaced to MSP430 G2553. This is an analog voltage sensor It is formed by a voltage divider circuit. It is also interfaced to MSP430. This is a N-type MOSFET, that is the MPPT switch. 3000 microfarad capacitors are used to filter out the output waveform. Here we see the working. At present, the output voltage of PV panel is 16.7 volts. As we switch on the MSP board, the boost converter activates and the output voltage is boosted. The initial perturbation is set to a duty ratio of 40%. Based on the insulation, the duty ratio and output voltages are altered corresponding to the values of incremental power. These are the output leads resulting from the MPPT. For implementing the microinverter, the output of the MPPT is given to the inverter input. These are the inverter inputs. However, for the testing of the inverter, we need a CRO. Therefore, the testing will be shown in the lab.
Now starting with the software implementation of the PNR algorithm. First, the MSP430 board was initialized and the value of current was read by the current sensor and the value of voltage was read by the voltage sensor. Then the power was calculated and a delay of 2 seconds was given. Then the power was calculated, T is equals to T plus 2. After that, the incremental power was calculated and then the 4 conditions are if the incremental power is greater than 0 or the incremental power is less than 0. If the incremental power is positive and incremental duty ratio is also positive, then the duty ratio was incremented by 1. And if the incremental power is positive and the incremental duty ratio is negative, then the duty ratio was decremented by 1. Otherwise, if the incremental power is negative and the incremental duty ratio was positive, then the duty ratio was decremented by 1. And if the incremental power was negative and the incremental duty ratio was negative, then the duty ratio was incremented by 1. After that, the values were stored for the next iteration.
This is the visual of the circuit used for the sinusoidal PWM microinverter. This is the control circuit and this is the power circuit. In the control circuit, first of all, we have LM555 high precision timer IC that is used for the generation of sawtooth waveform of 6 volts and 450 Hz. The output of this timer is given to a buffer. The buffer is used so as the timer is not overloaded. The buffer is formed using the OPA277 IC of Texas Instruments. For the reference sine wave, we have a transformer 230 volt upon 12 volt. The output of the transformer is given to a full wave rectifier so as to obtain the absolute value of the sine wave. Next, we have two comparators, comparator number 1 and comparator number 2. Comparator number 1 compares the instantaneous values of sine wave and the sawtooth, and the output is given to a 7408 IC, that is the AND gate. This is the zero crossing detector. It detects the zero crossing of the sine wave and the output is given to the NOT gate. Based on the outputs of AND gate and the NOT gate, the switching is decided for the power circuit. Next, we have a look at the power circuit. This is the power circuit. Here you can see the H bridge of MOSFETs which are used as switches for the switching of DC into AC, and these are the MOSFET drivers, that is the IR2110 drivers. Based on the outputs of the AND gate and the NOT gate obtained, these are switched so as the DC is converted into PWM sinusoidal wave. Now let's have a look at the CRO output so as to see the sine wave obtained. This is the DC power supply. In the real world, this power supply would be given by a solar panel. It is set for a DC voltage of 12 volts so as to simulate the actual functioning of the solar panel. Here I set it to 12 volt. The output of the H bridge is connected to channel 1 of the CRO. Now, if I switch on the CRO, you can see the filtered version of sine wave, as we have used the RC filter for the filtering of the sine wave. This is the sine wave that is obtained. It shows channel 1 of 5 volts, that is, it is 10 volts peak to peak. Now for the frequency, the time base is set at 10 millisecond, and you can see it occupies only 2 blocks, which means the frequency is approximately 50 Hz.
We have tried to implement a complete solution from effective harnessing of solar power to its commercial usability. This system can be transformed into a grid interactive system if smart metering and PLL logic are also incorporated. Future work can also be done in the area of extending communication interface like GSM or Zigbee to the inverter, as these interfaces are low cost and suitable for small scale applications. This would encourage more consumer interaction with the utility, making it possible the concept of distributed generation. As we come to the end of video demonstration, we would like to extend our gratitude to our faculty mentor, Mr. Mohammad Anas Anis, and would also like to acknowledge Department of Electrical Engineering.